I would like to talk about phase transitions in inhomogeneous random graphs and in coagulation processes from a large deviation point of view. And this talk will be mainly based on an ongoing joint work with Wolfgang König, Heide Langhammer, and Robert Patterson, Diaz. My idea is to divide this talk somehow into main parts. In the first part, I will present you our results on inhomogeneous random graphs from the large deviation point of view. So our results on large deviations for this type of graphs. And I will try to explain you what we mean when we say that we want to look at the phase transition from the large deviation point of view. And in the second part of the talk, I will try to give you some motivation on why we decided to study such models to deal with coagulation processes, presenting what we already did and what we would like to do and to extend on the study of the phase transition in coagulation processes, always looking at everything from this large deviation point of view. So let's start with the definition of the model. So we are dealing with sparse inhomogeneous random graphs. Inhomogeneous random graphs are a very natural generalization of the famous Erdos-Renyi random graph. The Erdos-Renyi random graph is this model where we have n vertices in a graph, and the presence of undirected edges between vertices is independent and depends on some probability p. This generalization was firstly introduced by Söderberg and then deeply studied in terms of the phase transition by Bollobash, Janssen, and Riordan. And it is very natural in a sense that it introduces different type of vertices. So we have the vertices of the graph that are characterized by a certain type. And depending on the type of the two vertices, we will have a different probability of observing an edge between these two vertices. Still independent, so the mechanism is the same of the Erdos-Renyi random graph, but we only have this generalization in terms of different type of vertices. So let's start first with defining the metric space S, which will be the space in which the vertices takes their own type. So each vertex will be characterized by an element of this metric space S, which is the type of the vertex itself. For the definition of the model and for most of the results of Bollobash, Janssen, and Riordan in terms of the phase transition, this metric space S can be fairly general. I will present you our results that are currently on S being a finite space, and we are extending this to a more general space. But so for the definition and for most of the property of the model, S is a very general space, but for our results, then I will specify that we will deal with a finite S. Okay, after defining the space, the type space, then we have, we introduce a probability measure on S, this probability mu, and this probability mu will somehow encode the proportion of vertices of each type R in the limiting graph. So in the limiting graph, we will have a proportion of vertices of each type that depends on this measure mu. And for a fixed n, so for a fixed graph with a number of vertices, which is n, we have a vector xn, which is the vector of vertices type. And that means that if we label our vertices in the graph, the vertex I will have a type which is xi. So this is simply what this vector of vertices type means. And the only thing that we ask, again, this can be random, it can be deterministic, it does not matter too much for most of the properties that we are interested in the graph. But the only thing that we really ask is some sort of compatibility condition. So we ask that in the limit for n going to infinity, mu n, the empirical measure of this vector of the type of the vertices, converge in some sense to the measure mu. So we have this, we are asking for this compatibility such that our sequence of increasing graphs is converging to a graph which has mu as a proportion of vertices of each type. And then we have the kernel. The kernel kappa is a symmetric kernel, non-negative, that will encode the tendency that two vertices of a certain type have to create an edge between them. Indeed, we define the sparse inhomogeneous random graph as being a graph for a fixed n with n vertices, xn being the vector of the vertices type, and the probability of observing an edge between vertex I and vertex j, it's exactly given by kappa of xi, xj. So these are the two types of the vertices, and we rescale everything by n. So kappa xi, xj divided by n. And of course, there's an infimum with 1 because it's a probability, but for large M, we always work with a symmetric kernel, which is also bounded. So for large N, this is basically negligible. And we say that the graph is in a sparse regime. So this is the definition. Without the scaling is the definition of an inhomogeneous random graph. And the scaling gives us the sparse regime. And it's sparse in a sense that the expected number of edges that we observe in the graph is proportional to the number of vertices that we have. So the expected number of edges is basically n times this quantity here, which is an integral of kappa with respect to mu. And we ask that basically the main property that we want this kernel to have is that this integral here is a finite quantity, when this is most of the main property that we ask. And this type of graphs are known to have a phase transition in terms of the emergence of a giant component. And this has been deeply studied in high probability setting. So with high probability, we observe a giant component. This has been studied by Bollovash, Janssen, and Riordan. Indeed, they proved that the phase transition comes in terms of an operator, P kappa mu, that is this linear operator here. It's a very simple operator. And in particular, the phase transition depends on a norm of this operator here. So the norm that we will denote by sigma kappa mu, it's this norm here. And in the case of S finite being finite, it will be the largest eigenvalue of a certain matrix. And the phase transition depends on the value of this norm here. In particularly, what we know is that if sigma kappa of mu is less or equal than 1, then the size of the largest component is negligible with respect to n. While when this norm is strictly greater than 1, then with high probability, the largest component is proportional to n. And we also have a way to quantify the size of this largest component, in particular to bound the size of this largest component, depending on a function rho. And this function rho here is the solution of a certain fixed point equation that involves the operator itself. And this fixed point equation has a non-trivial solution. So 0 is always a solution of this fixed point equation, but this equation has also a non-trivial solution if and only if sigma kappa of mu is strictly greater than 1. So these are the results in terms of the phase transition that Bollovash, Janssen, and Riordan have. And these are all results in a sense of a law of large number sense. So these are with high probability. And what we would like to study is the graph itself from a large deviation point of view. And we would like to recover the same, so the phase transition that we know it's there from the properties of the large deviation function. So what we have to first identify are the quantities that we are interested in studying from a large deviation point of view. So what we decided to study are the connected components of the graph. We are not fully describing the graph itself. So we are not describing, for example, the number of edges, the number of triangles, or other properties of the graph. We will just focus on connected components. And from now on, everything that I will say will depend on a finite S. And when we have a finite S, that means that connected components of a graph can be identified by a vertex in n to the s, by a vector in n to the s, and this vector will tell us, so the R component of the vector will tell us how many vertices of type R we have in the component Ci. So this is what this vector type of Ci means for a connected component. And since we would like to study properties from a large deviation point of view, it's completely reasonable to introduce an empirical measure. We call this empirical measure the microscopic empirical measure, and it is rescaled by 1/n, where n is the total number of vertices that we have in the graph, and it puts the delta on every vector if there is a component of the graph that has exactly that component vector. So here we are summing over all the connected components on the graph, and here the delta is on types of Cj for each jth component. This measure here is a random measure, and it belongs to a sum set of measures that we call n of mu n. This is the set of measure lambda on n to the s. And we ask for that this measure satisfies some sort of compatibility condition. What we would like to have is that the total measure lambda and of course the empirical measure mi of n, they fully describe all the vertices and all the connected components of the graph. So what we want is that the total vertices of a certain type in any component of described by this measure is exactly the total number of vertices of that precise type. So this is why we ask this condition on the what we call the total mass of lambda. So for any measure lambda, C lambda will be a measure on S, and this measure will tell us that C lambda of R is the total number of vertices with type R. So this is why we are asking this to happen. And the fact that this empirical measure fully describe the system in terms of these connected components, and we are rescaling the number of these components, so the frequency of each component, because we are somehow imagining that small microscopic components, they appear rather often in the graph. But what we also know is that when there are some large components, they do not appear very frequently. So they are in frequency, they have a very small frequency. So dividing the frequency by 1/n will just make them disappear. So what we introduce is a second quantity, is a second empirical measure that we call the macroscopic empirical measure. And this empirical measure will be again summing over all the connected components, but now we are not rescaling the frequency of each type of connected component, but we are rescaling the size of the connected components itself. So here we sum again over all the components, but we rescale the vector types of Cj with 1/n. This macroscopic component, again, it's a random element of some set of measures, and this is the set of measures to which n belongs. And again, these are measures with integer values on 0, 1 to the s, because it's describing the number of large components proportional to n. Again, we are asking the compatibility condition, so we are asking that ma of n fully describe the system, and this is the space in which we imagine this ma n to belong. And if we look at these two measures, it's clear that when n is fixed, any of the two fully describe the system. So in principle, there is not really the need to take into account both of them. But what we expect is that in the limit n to infinity, what will happen is that these two measures, somehow they will decouple and they will represent two very different properties of the graph. So me, the limit of me will describe the frequency of microscopic connected components that we see in the graph, and the limit of ma will describe the number and the size of large macroscopic components that we expect in the limit. And what we think is that these two quantities, they will coexist in a limit. So if we want to study the large deviations of the connected components of our graph, we have to consider them together. And in order to consider them together, we have to enlarge a bit more the spaces that we are interested in, and we have to allow these two measures to belong to spaces where the total mass, either of the microscopic components or the macroscopic components, they are not constantly equal to the full mass of the vertices, but they can also be strictly smaller, because what we expect is that in the limit, the sum of the two will encode the total number of vertices that we had at the beginning. So we had to ask for this lesser equal instead of the equal. And in principle, these are the two spaces. So these two spaces are the ones in which we want to prove a large deviation principle. We endow them with a topology of convergence of integrals with respect to compactly supported functions, and then we consider the product space of the two. And what we want to prove is a large deviation principle for the pair me n and ma n exactly in this space. So roughly speaking, what we would like to have is to prove that there exists a function e from n times m to 0 plus infinity, 0 and plus infinity included, such that when n is large, the probability of our pair of empirical measure to be close to any pair of micro and macro measure lambda and alpha, it's roughly e to the minus n times this function e. And this function e then will tell us that the probability will decay exponentially in n when n goes to infinity, and it will tell us the property, so the probability of observing some rare event, but not only, because the minimum of this function I will also give us the most likely configuration of the system itself. So we expect that once that we have the function e minimizing this function e, will tell us also what are the most likely configuration of the event, going back to some law of large number type of result. And this is indeed what we can prove. So we can prove that the pair so microscopic and macroscopic empirical measures does satisfy a large deviation principle. And we even have the rate function in a very explicit form. What you can see here, it's not very explicit. It's basically because it's very complicated, and it's not, so for the sake of this talk, it's not interesting to have the full description of the rate function. But what I would like to tell you is that first, we can reorganize this I function into basically 4 terms, and one of the terms will simply only depend on the microscopic measure lambda. And this is why we call this I of me. Then there is another term that only depends on the macroscopic measure alpha. Another term that we call me, because somehow this is what we expect to represent the mesoscopic quantities of the system, because we are not really asking that these pair lambda and alpha fully describe the system. There's still the possibility that there is some mass missing, and this mass missing is what we denote as mesoscopic. And this is what the argument of this other parts of the rate function, and then there are a lot of constants. And the most important thing is that first, any pair of measures such that the sum of their total mass is not upper bounded, so dominated by the measure mu, has a rate function which is equal plus infinity. That means that we cannot choose pair of microscopic and macroscopic measures such that they sum up to something which exceed the proportion of vertices that we have in our graph. This is, of course, impossible because we only have these proportion of vertices, and we cannot ask for the limit to have something different. But of course, the sum of the two does not have to be equal to mu. It can be strictly less to mu, and this will just end up in the mesoscopic part. And then we have one single term, which I want to give you in an explicit form, because this is the term that we believe is the most important. And the most important term is the microscopic one. This microscopic one is given in this entropy form. So it's the sum or an integral in the continuous case of lambda k log lambda k over something that depends on k. And so this term here is the term that we think, and then we will even prove, that gives the phase transition itself. So this is the most important term when we want to focus on the existence or not of the phase transition. Then, of course, also the other terms are also important in terms of describing the full system. But if we want to focus on the fact that there exists or not the phase transition, we believe that it's enough to study this first microscopic term. And the good thing is that this term is the easiest one to get. So this is also the reason why we somehow want to focus first on this. Okay, so this is somehow the explicit part, the rate function, and at least the part which is most important to look at. Just to give you the key points of the proof, what we are doing here is a proof that is mainly based on combinatorics. So we're really estimating quantities. And the most important thing is that we first isolate and we kind of identify thresholds. So we fix a finite R and a positive epsilon such that we will call microscopic every component which has a size which is less or equal than R. We will call macroscopic any component which has a size which is greater or equal than epsilon times n. And what we will need in order to get our large deviation principle is to find accurate estimates of the probability of being connected of smaller graphs. So somehow when we do this cutting, we define these two thresholds, and what we need is to find very good estimates for the probability of these small components to be connected. And these are highly non-trivial, and they are very different if we are looking at microscopic component or at macroscopic component. And so this probability is the probability of being connected of a graph in general. But the good thing is that we don't need it for any type of connected component, but it's enough to have good estimates for these two regimes, so micro and macro. Then for everything else, it's enough to have an upper bound, some upper bound on this, again, this probability of being connected, because then there are a lot of combinatorial terms that basically they do the rest. They help in controlling what we cannot control by good estimates. And what we have to do is to first, after having identified these estimates and the real combinatorial terms, we first take the limit for n going to infinity, and then after we take the limit for r going to infinity and epsilon going to 0. And this is basically a small idea of how the proof works. And this is the estimates for this probability are the most important part. Okay, But what we want to say is to say something about the phase transition. So now that we have this very complicated but explicit rate function, we want to study the phase transition. And I want to recall that the existence of this phase transition was already proved by Bollo, Janssen, and Riordan. It's in terms of the largest eigenvalue of this positive matrix here, with matrix with positive entries. And we know that when this eigenvalue is less or equal than 1, then there is no macroscopic component. When it's strictly greater than 1, there is at least one macroscopic component, and the solution of this fixed point equation is giving us some hint on the size of this connected component. And let's go now to our rate function, and let's try to see if it's true that our microscopic rate function is studying our microscopic rate function. It's enough to identify the existence of such a phase transition. So we would like to minimize this rate function here. And what happens is that when sigma kappa of mu is less or equal than 1, so the largest eigenvalue of that matrix is less or equal than 1, for any measure on S, and in this case, this is basically a vector that we can identify, which is dominated by mu. So, and this means that if we fix a vector C, which is dominated by mu, so it's strictly or smaller or equal than mu, and we ask the graph to put that precise proportion of vertices into microscopic components. So if we ask that our limiting measure lambda has a total mass which is exactly equal to C, then for any C, we can find an optimizer. So we can always find an optimal lambda that we call lambda star of C, such that this is the argument of the infimum of the microscopic rate function. So it's always optimal to minimize the rate function over measures lambda with a total mass which is equal to a certain C for any C that I can prescribe. And in particular, we can also identify which is this optimal configuration. So the optimal configuration is this lambda star that we have explicitly. And this means basically that any microscopic mass is possible. So if I decide a proportion of vertices that I want to put into the microscopic mass, any proportion that I decide, any C, then it's always possible for the graph to optimize itself in this way, such that it's putting this precise proportion of components of a certain size. On the other hand, when sigma kappa of mu is strictly greater than 1, if I identify, so if I fix a proportion C, which is still dominated by mu, so in principle it's still possible, but such that its sigma kappa of C is greater than 1, then what we can say is that the rate function does not admit a minimizer into this set. So I can identify some proportion of mass that it's completely possible to have. So it's something that it's not that is prescribed by mu, but such that its eigenvalue is strictly greater than 1. Then for the system, it's impossible to organize itself according to this mass. And in particular, it's always possible to identify a sequence lambda of n, which is minimizing this rate function here. So along this sequence, this is constantly decreasing, but this sequence here has a limit which does not belong to the set n of C. So the limit of this function is belonging to another set. So it has total mass which is strictly less than the prescribed mass C. In particular, this mass, so the form of this limit is exactly the optimal form that we had before, but the total mass of this limit is strictly less than the prescribed C. It's a B star, which depends on a function f. So this B star is 1 minus f times C, and this f is a positive non-trivial solution to a certain fixed point equation. And this fixed point equation is again a fixed point equation that involves the operator T. And it's again a fixed point equation that admits a non-trivial solution if and only if sigma kappa of C is strictly greater than 1. But this is different from the fixed point solution that we had from Bollobash, Janssen, and Riordan. So this is somehow telling us that if we are simply looking at the microscopic the microscopic rate function, not every microscopic mass is admissible. So I can identify a set of microscopic total masses that won't be accepted by the system. So the system is not able to organize itself in an optimal way if I prescribe this microscopic mass. And indeed, what the system is actually doing is that it's basically organizing itself according to some measure that is pushing the excess of mass away, and it's organizing a B star mass in the best possible ways that it can, and it's pushing everything else into the mesoscopic part. So it's a sort of saturation effect. What's happening here is that I'm trying to put a mass that is too large for the system to be handled, and what the system does is just pushing away something and organizing the B star mass in the optimal way. So this is telling us that already by looking at this microscopic rate function, we are seeing the phase transition, and the phase transition is exactly in terms of this saturation effect. But this is not telling us what's happening to the graph itself, because we know that the graph also has some additional parts. So the rate function depends, that had also some other additional term. And only minimizing the full rate function will give us the optimal configuration of the system. And this is indeed what happened. And when we minimize the full rate function, we recover the Bollobash, Janssen, and Riordan fixed point. And indeed, this is, so here it's written with the K reducible, meaning that all the types can be connected one to the other. And we can identify the minimizer of the rate function, and it's a minimizer that has one single giant component, which has a mass which is proportional to rho times mu, and rho is the solution of the fixed point equation from Bollobash. And everything else is organized in lambda star, in the optimal microscopic mass. But so basically we recovered the law of large number results of Bollobash, Janssen, and Riordan. We also realized that it's optimal for the system to put a mass which is actually smaller than the maximum admissible mass, because we knew from minimizing the microscopic rate function that there was a threshold that was that B star, that was the maximum possible mass that we could organize in microscopic parts. But indeed, the optimal microscopic mass in the graph itself, it's strictly less. So while the sigma of the optimal mass for the microscopic was exactly equal to 1, so it was at the boundary of the admissible region, in the graph, we have that the optimal mass is strictly inside the admissible region. And that means basically that the macroscopic mass, as soon as it's there, it's changing a bit the equilibrium, and such that as soon as I have the phase transition comes as a saturation effect. But as soon as I have a macroscopic mass that is kicking in, then the equilibrium are different, and it's always optimal to put a bit more in the macroscopic component and strictly less than the maximum admissible in the microscopic one. So this is somehow the full minimization of our rate function and what it's giving us and how it's going back to the results of Bolloba, Janssen, and Bjorka. And what we would like, and we are basically doing, is trying to extend it. So this was working perfectly for finite S, but we have a very natural definition of all our quantities and also a natural extension of our rate function in the case of general S. And what we are trying to do is to extend this by using exponentially good approximation. And that means that what we want to do is to take a general S, to discretize it, and discretize also the kernel kappa on it. Just for a fixed M, we consider a sequence of discretization, and what we want to prove is that these discretization are exponentially good enough. That means that when n goes to infinity, this probability of the two discretization to be different one from the other is decaying faster than exponential. And as soon as we can find this, then also all our results will hold for a general S. And the idea of considering a general S is basically because we would like to extend these to coagulation processes. And this goes back to what I would like to mention also here as a motivation and a reason to study this type of graphs, which is the connection with coagulation processes. And we call coagulation processes these processes in which we have particles provided with a certain mass, and this particle, depending on a rate that we call f of xi and xj, they merge together in a larger particle. So this is in general what one calls a coagulation process. So a process in which we have particles with a mass, they come together into larger particles. This is a very natural and well-known process. It was introduced from a deterministic point of view by Smoluchowski, and by writing the Smoluchowski coagulation equation. And let me just briefly tell you that, so this is the Smoluchowski coagulation equation, and it's an equation that describes the evolution in time of the density of particles of a certain mass. And the most important initial condition that one can consider is what it's usually called the monodisperse initial condition. And it's the case in which we start with all the particles of mass 1 and we let them come together according to this coagulation rule. It's known that this system can have a phase transition. And the phase transition in this case, it's called gelation, and it's basically, it's the case in which, so we call gelation time the time in which the second moment of this measure explodes, and the phase transition happens, letting time evolve if this gelation time is finite. And the interpretation is that after the gelation time, the first moment of this density is not conserved. That means that basically we have some mass which is living in an infinite mass particle. Okay, so these are the coagulation processes from a deterministic point of view. One can describe the same thing from a stochastic point of view by describing a Markov chain, a Markov process in which we have particles coming together, and this is what it's usually called the Markov-Shlushnikov model. Again, we have particles of a certain mass. We can index everything by the total mass n, and the monodisperse initial condition will be that these particles at time 0, they're constantly equal to 1. We have a coagulation mechanism, which is simply the rate of this coagulation to happen, and this will depend on a certain measure, on a certain function f. And at this level, the phase transition, it's a bit less clear to know what this is, but basically the gelation means that at certain finite time, we have some giant particle, which is really close to the giant component that we have in random graphs. And indeed, what we already studied is that when one chooses one particular type of kernel, which is the multiplicative kernel, then first of all, this type of kernel does show a gelation phase transition, and it's also known the time of this phase transition to happen. And the other thing is that this coagulation model with this multiplicative kernel have a one-to-one description with the connected component of the simple Erdős-Renyi random graph. Basically, the vector of particle sizes is in one-to-one correspondence with the connected components of these Erdős-Renyi random graph with probability of observing edges equal to 1 minus c to the minus t over n. And again, that means that the gelation phase transition corresponds to the phase transition of the random graph in terms of the emergence of a giant component. And now we can go back to what I described at the beginning of the talk, which is the large deviation for an inhomogeneous random graph. But in this case, we are even in a simpler case, because here we are in the case of a simple Erdős-Renyi random graph. So the type of the vertices is all the same. And that means that we can write explicitly the phase, the rate function. And here I actually wrote the real explicit rate function in this case. This is what we have. It depends on t, because now the parameter that is driving our phase transition is the time. So it's time dependent. And it has this form. And again, we can see the entropy form term, and this is exactly the term that is giving us the phase transition. So when t is less or equal than 1, we can minimize this term, and when t is greater than 1, we cannot. So this is again the presentation of the rate function of the system, and underlying that the phase transition only depends on a small part of the rate function. And just to tell you, to add very briefly that we believe that this happens also in very different models. One can write also the rate function for the coagulation process when the kernel is additive. So this is a way slower process. This is the explicit form of the rate function. It's very easy to get. It's just a matter of taking some limits. But again, we have an entropy form term. And this entropy form term can always be minimized. And this is telling us that there is no phase transition in this case. And this is exactly what it's known, because the additive kernel in coagulation processes doesn't gelate. So it does not have a phase transition in time. And this is exactly seen again by the entropy form of the rate function itself. And to conclude very briefly, also condensation type of, so models that show condensation type of phase transition, they often have a rate function that has an entropy term form. For example, we can write a system, so for example, there is the Becker-Doring coagulation fragmentation model, and there is, for example, the Bose gas without interaction, for which the partition function is known. The partition function takes this form because we can rewrite all the model in terms of cycles, of empirical counts of cycles. But the most important thing is that this partition function is such that one can compute the free energy. The free energy will take this form, and it will depend on a function I, which exactly take an entropy form. And indeed, it is known that when the dimension is less or equal than 2, then this function can always be minimized. There always exists a minimizer for any density that we prescribe to this system. And when D is greater or equal than 3, then this is not true anymore. And this is exactly what it's known to be the phase transition in the non-interacting Bose gas. So when D is less or equal than 2, there is no phase transition, while when D is greater or equal than 3, then this is what happens. So there is some threshold, so some maximum density rho star, such that when one prescribes a density which is greater than this rho star, then we cannot minimize this function here over measures with that prescribed density. And this is again the same type of behavior that we observe in the impossibility of being minimized of the rate function. And just concluding, this is what we would like to go on applying to other models to try to describe different type of phase transition in terms of their rate function, and also to try to use this to study more general coagulation processes using inhomogeneous random graph, adding some spatial components. So this is why we want the type of the vertices to be general, because we would like this graph to be embedded in, for example, some Euclidean space, considering other coagulation kernels, so not the multiplicative one with the Erdős-Renyi random graph, or describing some different graph processes. And with that, I thank you for the attention, and I'm sorry if I may be a bit late, and thank you.